Good evening, Ireland. It's a pleasure to be back to talk to you here about warping space and time. I'm going to give you a little bit of a brief history behind black holes and then spend a bit of time talking about science fact and a little bit of time at the end talking about science fiction and then thinking about where things go in the future. So firstly, a brief history. Let's just make sure we're all on the same page as to what we're talking about. A black hole is a region of space from which nothing, not even light, can escape. And the idea, the concept of a black hole probably goes back earlier than you think, right back to 1783, when the Reverend John Mitchell commented, well, if we had a sphere the same density of the sun but larger than the sun by a factor of 500, then all light emitted from such a body would be made to return toward it by its gravity. In other words, if an object is large enough, light would not be able to escape. So this concept has been around for hundreds of years. But in the 1800s, the idea of such a star that couldn't emit any light, a so-called dark star, well, during the 1800s, this was all but forgotten. But of course, in the 1900s, there was a resurgence in the whole idea because of Einstein and his general theory of relativity, which was then picked up by a number of different people. I'm not going to talk through the details of all of their contributions, but each of these people had something to contribute by taking Einstein's general theory of relativity and saying, what would happen if you had a dense enough object? For instance, what would happen if a star collapsed? And it was realized that A, this is theoretically possible, though it was not known at the time whether or not we'd ever be able to observe a black hole. It was known that this was a theoretical possibility according to Einstein. And not only would they say, okay, it looks like very odd things will happen, for instance, distortion of space, but also there'll be a distortion of time. And it was predicted that actually, when you form a black hole, time will stop. So that's why we're talking about warping space and warping time. Very odd things happen when you generate a very concentrated mass, such that light cannot escape from that region of space. So we're going to need to cover a few pieces of the puzzle to make sure we understand the various aspects of black holes. And I've labelled each of these aspects one of the colours of these jigsaw pieces. We're going to look at the concept of escape velocity and then dabble with a little bit of general relativity, by which I mean we are not going to deal with the maths. As David said earlier, that's not what this talk is all about. We'll mention some of the ideas behind general relativity. We'll have a think about how stars and galaxies might form black holes, and we'll think about how you can go about detecting them. So those are the four strands, and we'll look at each of these pieces of the puzzle in turn, and hopefully those four strands will pull together. To try and make it more sensible, I'm using these little coloured jigsaw pieces in the top left-hand corner so that you can hopefully remind yourself which particular section we're dealing with, and I'll make handouts of these slides available to you afterwards, and again the coloured jigsaw pieces will be in the top left of the handouts so you know which particular aspect we're dealing with. So let's start with escape velocity. So the escape velocity of a body, such as wanting to escape from the surface of the Earth or the surface of the Moon or the surface of essentially any body, because gravity is holding you back, there will be an escape velocity, meaning if you throw something fast enough, it will eventually leave the gravitational influence of that body. It actually doesn't matter which direction you throw this object. If you throw it fast enough, if you reach escape velocity, it will leave the gravitational influence of the body you're standing on. And the escape velocity calculated for any given body, let's assume that we're on the surface of a spherical body because that just makes life easier. The escape velocity only depends on the ratio of the mass to the radius of that body. In other words, the mass of the body we're standing on and the radius, in other words, the distance that we are standing from the centre of mass of that particular body. And it's only that ratio that matters. It doesn't really matter what the maths is, it's just that ratio that we're going to think about, the ratio of the mass to the radius. If we put in some numbers and calculate an escape velocity for instance, on the surface of the moon, how far would we have to throw an object in order for it to leave the moon? Makes no difference what the mass of the object is, it's the mass of the moon that matters and the radius of the moon. And the escape velocity from the surface of the moon is 2 kilometers per second, or in old money, 5,000 miles an hour. The escape velocity from the Earth is about 11 kilometers per second, or 25,000 miles an hour. So that's how fast the Apollo astronauts or the Artemis astronauts had to go in order to leave the influence of the Earth and get to the moon. The escape velocity from the surface of the Sun, very much larger mass, yes, a larger radius, but the larger mass outweighs that and gives you a rather high escape velocity of 600 kilometers per second, or more than 1 million miles an hour. And that might sound ridiculously fast, but bear in mind that even that is only a tiny fraction of the speed of light. It's barely 0.2% of the speed of light. But we can do a thought experiment and say, well, what if, we don't know how to do this, but what if we could compress the sun? We keep the sun's mass, but we simply squeeze it into a smaller volume. What would happen to the escape velocity? Well, if the escape velocity depends on the mass divided by the radius, then that's where we are at the moment. That's the radius of the sun, about 700,000 kilometers or thereabouts. And the escape velocity we just said was 600 kilometers per second. What if we were to take the sun and compress it so the same mass is now in a smaller sphere? Well, because the escape velocity depends on mass divided by radius, we're keeping mass fixed and we're making the radius smaller, so the escape velocity goes up. If we make the sun even smaller, the escape velocity goes up again, and so on and so on. If the sun was only 30 kilometers in radius, it would have an escape velocity of 100,000 kilometers per second. And the limit of this idea is if we take the radius of the sun down to 3 kilometers, then the escape velocity reaches the speed of light. In other words, no light can escape from this object. If we squeezed it any smaller, we would still have a situation where no light would be able to escape. So that point, the point at which we say we've squeezed the sun down to a radius of 3 kilometers, we've now generated an event horizon, a one-way surface, if you like, or membrane. Objects can fall in, but nothing can come out. We call this particular radius the Schwarzschild radius because of the work of Schwarzschild in the early part of the last century. So that's a theoretical experiment. If we simply take the sun and squeeze it, we can make a black hole of radius 3 kilometers. But what if we started with a body with a different mass? If we wanted to make the Earth a black hole, we would take the mass of the Earth and compress it down. Well, we'd have to compress it down to something the size of a marble. If we got the radius down to a size of order centimeters, then we would generate a black hole. For the moon, we'd have to compress it down to something smaller than the size of a grain of sand. And if we took a mass equal to the mass of Mount Everest, well, we'd have to compress that to the size of an atom before we turned Mount Everest into a black hole. Of course, we have no idea how we could actually do that, but that's a technological challenge. The physics says we would generate a black hole if we made these masses small enough, simply from our understanding of the escape velocity depends on the mass divided by the radius. Okay, what do we understand from what Einstein said back in the early part of last century? Well, that's Einstein's general relativity reduced to the simplest equation I can think of, and I am not going to explain what that actually means. Not surprisingly, it hides an enormously complex set of concepts. But in essence, what it means is the geometry of space on the left is related to how much mass and how much energy is in space. That's on the right-hand side. Now, when we talk about the geometry of space, well, we have to think about what do we actually mean by that. And in order to get a gut feeling for what this equation is actually telling us, some people have said rather prosaically, you can reduce it to, well, mass actually tells space how to curve, and space tells mass how to move. Maybe that helps, maybe that's just more weird words that doesn't actually tell us what's going on. But the bottom line is the presence of mass, strictly speaking mass energy, in space distorts space and makes it change its geometry. And as a result of that changed geometry, that determines how objects move through space. But what do we mean by curved space? How can we talk about space changing its geometry? That's a difficult thing for us to get our head around because we think of space as simply being nothing, as simply being the gaps between the stars, for instance. The only way we can really imagine what's going on is to use some sort of analogy. And the usual analogy is to say, well, let's imagine that space was actually two-dimensional, and then let's think about distorting space by curving it into the third dimension. Well, that works up to a point, but then when we say, yeah, but how does three-dimensional space actually behave? Well, we then have a problem because we can't really imagine that. Because we can't simply say, let's take three-dimensional space and start wrapping it into the fourth dimension, because we simply are not born with the imagination to allow us to think, how does three-dimensional space curve into the fourth dimension? So we're left with the analogy that the best we can do is to say, imagine that space is actually a two-dimensional sheet. You've probably heard of this before. Imagine it's a sort of rubber sheet that's extensible, and then we can distort this. For instance, if we generate a black hole, then it's like putting this infinitely distorted funnel into two-dimensional space. Now, that's a limited use because we can't easily extend that to 3 dimensions. But that's why all artists' impression of a black hole end up looking like a funnel, because we've reduced it to what would a 2-dimensional black hole look like if we could imagine it distorting space into the 3rd dimension. So it's always a bit of a problem. Einstein's theory says mathematically this is how you deal with it, but our imagination is somewhat limited, and that's why it's difficult for most of us to figure out what Einstein was actually saying in his mathematics. There were various predictions of general relativity, and when we say Einstein predicted that in principle if you had a large enough concentration of mass you can generate a black hole, well, why should we believe that? Well, it's basically because general relativity has proven itself in lots of other areas. For instance, when we look at how Mercury orbits the Sun, it's been known for some time that the elliptical orbit of Mercury precesses, and as indicated by the movie on the left or that graphic on the right. The closest approach of Mercury to the Sun, the perihelion, changes slightly. Newton figured out it would do that, but didn't quite get the calculation right. Einstein's general relativity effectively gets the prediction of the precession of orbit of Mercury effectively spot on. Similarly, it's been known that if you look at stars as the starlight grazes the surface of the Sun, that starlight is bent slightly. The beams are not perfectly straight. Again, Newton knew about this. Newton predicted that star positions, when starlight grazes the surface of the Sun, they'll be slightly off position, but again it didn't calculate precisely how much they would be off by. But general relativity, when tested during an eclipse, so we could see stars when they were in a position to graze the surface of the Sun, the positions of those stars were shifted from their known positions by an amount that Einstein predicted correctly. So we have some faith in what Einstein is telling us. Not only do we believe everything he says about how the existence of matter and energy distorts or warps space, but the predictions of general relativity also said that it'll change the way time flows. Time will slow down in a gravitational field, and indeed, in a very strong gravitational field like that just outside a black hole, time will essentially stop. We can't show that directly, but we can do some experiments here on Earth. So, for instance, some atomic clocks were carefully synchronized and then placed in an airliner and flown at different heights and at different speeds in different directions to verify the results not only of special relativity, saying that time slows down depending how fast you're going, but also the effects of general relativity by flying at different heights from the surface of the Earth, and a clock being left at ground level as a reference. We now know that we need to compensate for these changes due to special and general relativity. For instance, in the GPS system, we're looking at atomic clocks that are beaming their time signals down from satellites. We have to take into account the fact that the satellites are moving, special relativity, and the satellites are at different heights above the surface of the Earth, general relativity, and we have to take those into account to work out corrections to the atomic clocks in each of those satellites in order to give us an accurate fix. If we want to know where we are to an accuracy of only a few meters, we need to apply Einstein's special relativity and general relativity. So we have lots of reasons to have faith in what Einstein is telling us. One of the predictions of general relativity is the existence of gravitational waves. If you have mass moving, for instance, one black hole orbiting another, you will generate ripples in space. Technically ripples in space-time, but let's think of them just as ripples in space. If those ripples in space travel through a cylinder, they will make the cylinder distort. Here, in a very exaggerated sense, a cylinder whose cross-section is circular will appear to be distorted in one direction and then distorted in the other, pulled in one direction and then pulled in the perpendicular direction as the gravitational wave passes through the object. But this cartoon exaggerates the effect enormously. Here the cartoon is exaggerating the distortion because it looks like a distortion of 10% or 20% or 30%. In fact, the ripples in space-time, we can only expect them to be of order 1 part in 10 to the power 20. Even if we have a very dramatic event like one black hole colliding with another, we would expect that over cosmic distances that would only give ripples in space-time that are that sort of order of magnitude. For a long time, it was simply assumed that they would be too small to ever measure, but more recently, we've actually developed the technology to do that. More of that in just a moment. The third piece of the jigsaw is, well, how do we expect black holes can be made? We can't make a black hole. We can't take a planet and compress it to the size of a marble, but gravity can do that on large enough scales. For instance, a massive star might end its life as a supernova. There's a number of different ways this can happen, but a supernova can generate the densities required. Some of the star's matter is thrown out, and some of the star's matter is compressed in the core and could, with a large enough mass in the first place, generate an object with a density with a large enough mass in a small enough volume to generate the conditions of a black hole. If we get too close to a black hole, we can predict what's going to happen. If a star gets too close to a black hole, the star might be ripped to pieces completely. Notice that the debris doesn't go straight down the plug hole. Even though the black hole might be capable of absorbing all the material of a star, just like when you let water out of a bath, the water doesn't all go down the plug hole instantly, it circulates around before going down the plug hole. Same sort of idea. Infalling matter, because of the conservation of angular momentum, will normally form a so-called accretion disk, where all the material is circulating around the black hole, slowly spiraling inwards, and it's the inner edge of the accretion disk in which matter is feeding into the black hole. Notice also that as well as generating this accretion disk, we seem to have some jets coming out from the two opposite directions. The accretion disk is basically the debris from whatever the material is, the star, the gas, being ripped apart by very large tidal forces. This is often referred to as spaghettification, or sometimes called the noodle effect. But the origin of these jets, we are fairly sure they exist possibly for every black hole when material is falling in, but we don't fully understand all of the mechanisms involved. It is widely thought that the very intense magnetic fields and the circulating black hole, the rotating black hole at the centre, are responsible for material being thrown out along the polar axes, along the jets. X-rays as well as particles accelerated close to the speed of light. But we are still studying these systems because we don't fully understand the mechanisms. When we look at the centre of our Milky Way, here's an ESO animation of observations that have been made over 10 years or so. A number of stars close to the centre of the Milky Way have been observed, and they have been observed to be following elliptical trajectories, which is what you would expect if they're orbiting something. But we can't see what it is that they're orbiting. There doesn't appear to be anything there, nothing that we can see directly. And yet, relatively large stars are being pulled and accelerated over very short distances, over a period of a few years. Now, simply using our understanding of how objects move, for instance, how one object orbits another. This is a multiple star system effectively, but if we treat it as lots of individual stars orbiting something at the centre of the Milky Way, we find that something must have a mass of 4 million solar masses in order to give us the behaviour of those stars. In this talk, I will stick to the convention that capital M, circle dot, means the mass of our Sun, simply because that's a more convenient unit than using tons or kilograms. So there seems to be something at the centre of our Milky Way with a mass of 4 million solar masses, but it must be relatively compact, otherwise the stars would have collided with it. It can't simply be a star cluster made of 4 million stars. That would be simply too large for these stars to be orbiting. If we think of the size of this object, for the scale, we've got the solar system here. Let me just make that a bit dimmer so we can see. This object must be larger than our Sun, but certainly smaller than the orbit of Mercury, as shown by the black dot on the left-hand side. That's how big we think the black hole at the centre of our galaxy is. Excuse me, just one second. We think that there are supermassive black holes. From here on, I'll use the abbreviation SMBH. We think there are supermassive black holes at the centres of possibly every galaxy. For instance, the Andromeda galaxy has got an even larger supermassive black hole, some 250 million solar masses, substantially larger than ours. And it would be something like the size of the orbit of Jupiter, as shown on the right-hand side there. The Sombrero galaxy has a supermassive black hole of 1 billion solar masses, and that would be a size more like the orbit of Uranus. I'm not sure what the record is at the moment, but I think the largest black hole yet found is somewhere in excess of 50 billion solar masses. And on this scale, well, it's a bit big for my diagram, so let's just bring it in from the side there. It would be absolutely enormous. Still only about the size of a solar system, of course very much smaller than the size of, for instance, a star cluster. It's thought that there might even be black holes at the centres of some of the star clusters within the Milky Way. For instance, the Hubble Space Telescope has detected what appears to be a massive black hole at the centre of the M15 star cluster. And there's a few other clusters, such as, for instance, the globular cluster Omega Centauri. That's a very large globular cluster, and again, it appears to have a rather massive black hole at its centre. Perhaps these are more common than we first thought. We've known about the one at the centre of our galaxy for a while, but now we're finding more and more black holes at the centres of star clusters within our galaxy. Let's think about the fourth element of what we're doing here, thinking about detecting gravity. Having dealt with escape velocity, general relativity, how black holes are formed, let's think about how black holes might be detected. A little over 10 years ago, gravitational wave detectors were brought into operation. They were in development for many years prior to that, but in the teenies, the LIGO gravitational wave detectors were brought online, as indicated here, 2 of them across the continental United States, one in Hanford, Washington State, and the other in Livingston, Louisiana. Each of them is an L-shaped interferometer, and you can see that they're separated by 3,000 kilometers. The idea being, if you detect something that you think is a gravitational wave, well, no one will believe you unless you can make an independent observation with an observatory that is some distance away, so that you're not simply seeing the same vibration of the ground or a door slamming or somebody's footprint. So that's what LIGO looks like, a laser interferometer gravitational wave observatory, LIGO. It involves a laser generated in this central building, and then the laser is split and sent down each of these 4-kilometer arms to a mirror which reflects it back to the central building. So there's a laser going off in 2 perpendicular directions, 4 kilometers, reflecting on mirrors and come back again. If those 2 arms are the same length, then the laser takes the same length of time to go down each arm and come back again, and the 2 laser beams arrive together. But remember what happens if a gravitational wave passes through material. It distorts according to that cartoon we showed before. It gets stretched one way and then stretched in a direction that's perpendicular to that. Any object would get stretched, including the arms of the LIGO observatory. So if a gravitational wave passes through LIGO, the 2 lengths of arms will go backwards and forwards, slightly longer, slightly shorter, slightly longer, slightly shorter. And so the light that would otherwise arrive back at the same time along the 2 arms will take slightly longer to go down one arm compared to the other as the gravitational wave passes through. And then a fraction of a second later, the 2 arms will swap over, one will become shorter, the other will become longer, and again there will be a time delay between the 2 arms, backwards and forwards, backwards and forwards. And if you use an interferometer to effectively measure very accurately either the phase or the timing at which those 2 laser beams arrive back after travelling down those 2 arms, you'll be able to tell if there's any tiny differences in the length. The light bounces off these 2 large mirrors at the end of the 2 arms. Each of the mirrors is suspended in a sort of a pendulum arrangement to try and isolate the mirror from any local vibrations, such as vibrations of the ground produced by people walking outside, or a car going by, or a train going by a few kilometers away. You have to try and reduce and eliminate all terrestrial sources of interference and possible signs of a vibration before you can be sure you're looking at gravitational waves. The laser beams are combined in an extremely complex interferometer, which I'm not going to attempt to describe. And back in 2016, the first results from LIGO showed that an observation had been made a few months earlier. It took them a while to analyse and be sure that they knew what they were looking at. The graphic at the bottom shows the signals in red and blue from the two LIGO observatories in Hanford and in Livingston. They interpreted these wiggles as being what we have seen is the merger of two black holes spiraling around each other and then merging together, and then a so-called ring down where the two black holes, as it were, settle down once they had merged. How do you determine that's what this is? Well, you can only say that this particular set of wiggles, which you might think is a very unimpressive set of noise, well, no. If you do the calculations, if you look at the theory of what would you expect from two black holes that are merging together, well, if we look at it individually from the Hanford data and the Livingston data, the bold line in each is the actual signal received from each of those LIGO observatories. And the thin line, which follows relatively closely, is what you would predict from two black holes merging together. So to start with, you don't see very much, and then you start to see an oscillation, and the oscillation grows in amplitude and gets faster and faster and faster, and then disappears. And the important point is that what you see in the Hanford detector is the same as what you see in the Livingston detector. Nothing, and then a signal that's growing in amplitude, growing in frequency, and then disappears. They are not perfectly synchronized. They're a few milliseconds different, because remember, these are 3,000 kilometers apart. If you're looking at a cosmic event, depending on where in the sky this cosmic event was, you can't expect the gravitational waves to arrive at the same point at the same time. So these have been shifted to account for the fact that one was a little bit closer to the source than the other. And if you lay the two on top of each other, yes, it's a little bit noisy, but there's an unmistakable signal in there which is growing in amplitude, growing in frequency, and then disappears. One thing to notice, two things to notice: the scale on the left-hand side, the strain is the fractional change in the lengths of these arms. The change in the length of the arm compared to the length of the arm. The strain was 10 to the minus 21, a ridiculously small effect. The other thing to notice is the time scale. All of this took place in a fraction of a second, just a few tenths of a second. And the interpretation of a growing signal with an increasing frequency is this idea of two black holes getting closer and closer together. As they got closer together, the strength of the ripples increased, and as they got closer together, they spun around each other even faster, and hence the increase in the frequency. The theory said that in order to model this particular change in profile of the signals, they determined that what we've actually seen is a black hole of mass 36 solar masses merged with another one of mass 29 solar masses. 36 plus 29, and you end up with a black hole of 62 solar masses. I hope you realise that 36 plus 29 does not equal 62. It equals 65. So somewhere along the line, 3 solar masses have winked out of existence. In a fraction of a second, 3 solar masses were converted from mass into energy, and that energy was radiated away as gravitational waves. It's been calculated that this particular event must have been about 1 billion light years away, and yet it was still possible to measure the ripples in space, even though these two black holes merged 1 billion light years away in another galaxy. For a fraction of a second, for the fraction of a second we're looking at over this timescale here, it's been calculated that the energy output of this pair of black holes was more than the rest of the observable universe put together. All the stars in all the galaxies that we can see were outshone temporarily by the energy output of this event. Absolutely phenomenal. And the technological challenge of actually building an observatory, an interferometer, that's capable of measuring such tiny changes in length is truly remarkable. And now more such interferometers are being built around the world, so we can get much more accurate ideas of how things are merging, neutron stars as well as black holes, and where in the sky they are, so that we can go and see whether or not we can follow up the observations with optical telescopes. The next stage of interferometer, it is planned, would be a space-based interferometer. Yes, we need to build a few more ones on Earth to start with, but ultimately there are plans to build LISA. The test technology has already been done, and they think it's possible. Put satellites up in space, move them away from the Earth, and send laser beams between different satellites. Here, not one large L, but a triangle of 3 satellites, each sending lasers back and forth, and then you try and station keep those satellites and measure tiny changes from the lasers bouncing back and forth between them. Instead of having an arm of kilometers in length, you would have arms millions of kilometers in length, and that would make you sensitive to gravitational waves of much longer wavelengths. So LIGO is good for short wavelengths and things that happen on a timescale of less than a second. For instance, black holes crashing into each other, or possibly neutron stars merging with each other. But LISA will, because of its much longer arms, be sensitive to much longer wavelengths and much slower variations. Things changing not over a fraction of a second, but changing over many seconds or minutes or hours. And it's hoped that that would mean that LISA would be able to detect signals from black holes at the centres of galaxies, very large, supermassive black holes. It might even be possible for LISA to be able to detect gravitational waves from the biggest singularity of all, the creation of the universe that would have produced ripples in space-time. Is it possible that LISA might be able to measure those? It's going to be a while before that's operational, perhaps sometime in the 2030s, conceivably even a little bit later. Meantime, we can use telescopes here on Earth. We can take a whole load of radio telescopes and use them in concert to actually give us a radio telescope effectively the size of the Earth, to give us the resolution to be able to see the accretion disk around a black hole. The Event Horizon Telescope was pointed towards the M87 galaxy to look at the supermassive black hole at its centre, called M87 star. What we think we're looking at in that is, if we think of this animation, this simulation, if we did have a accretion disk, even though it might be actually a pancake like Saturn's rings, it would look rather different simply because of the distortion of the gravity of the black hole at its centre. So you can imagine that if you are looking at Saturn's rings, it's very much distorted, because at the top you can see the back of the rings over the top of the black hole, and at the bottom you can see the underside of the same accretion disk, because again the light has been distorted and bent by this black hole. So we are looking at light coming from both sides, the top and bottom of the accretion disk, and that gives us this rather distorted view. Notice also it's a little bit brighter on one side than the other, simply because some part is rotating towards us and some part is rotating away from us. And that's why we get this sort of effect. It looks almost like we're looking at a donut face on, but even if we were looking at an angle, we would still get the same sort of impression, a little bit of a shadow in the middle because of the way light is distorted around the black hole, and we tend to get variations in intensity because of the way the accretion disk is rotating. So in this particular galaxy, it's a very large galaxy, and it has a supermassive black hole estimated at 6.5 million solar masses. This galaxy was one of the targets of the Event Horizon Telescope. Because it was such a large galaxy with a large black hole, we thought we'd have a chance of imaging the accretion disk. But at the same time, they also took data from the centre of our galaxy, Sagittarius A star. It's a lot smaller black hole, only 4 million solar masses, so something like 1,000 times smaller. But the centre of our galaxy is about 1,000 times closer than the M87 galaxy. So much smaller but much closer, as it happens, a similar size in the sky. It's a little bit different. It seems to have more structure in it, and for this particular one we've managed to get some impression of what the magnetic fields within the accretion disk might look like. Again, understanding the magnetic fields will help us understand how matter circulates in the accretion disk and how it falls into the central black hole. A reminder that the sizes are very different. Even though they look similar sizes on our sky, the actual size of the M87 accretion disk, here it's placed relative to the orbit of Pluto, so you can see the accretion disk of M87 star is huge compared to our solar system, much larger than the orbit of Pluto. Just for scale, that's an indication of how Voyager 1, the distance that Voyager 1 has left the centre of the solar system. If Voyager 1 started from the centre of this accretion disk, it would barely have got to the inner edge after 50 years. And the accretion disk around Sagittarius A star, very much smaller, here shown relative to the orbit of Mercury. You can see that the accretion disk around our supermassive black hole is small compared to Mercury's orbit. Again, that just reinforces this 1,000-fold difference between the size of the accretion disk of M87 and Sagittarius A star. These black holes are very different in size, but you could argue the accretion disks look qualitatively very similar. Does this mean black holes of different sizes all appear to behave in very similar ways? Well, we've had a look at some of the science facts behind how black holes are formed, how accretion disks are formed, and how we go about observing black holes. Let's have a think about some of the science fiction. Does Hollywood ever get it right? There's been lots of films that involve black holes. I've just picked out 3 for a bit of fun. One is Disney's film, The Black Hole, with Maximilian Schell and Ernest Borgnine, etc. Here we have a ship parked right next to the event horizon of a black hole. Time effectively stands still just outside a black hole, so you can basically just park there quite happily. That's the idea of the black hole. In Lost in Space, well, they're trying to escape from a planet, and the ship is pulling away from the planet and appears to be going fast enough to escape the pull of the planet, but then the planet seems to collapse and it collapses into a black hole, and suddenly the ship is pulled backwards. The third one is Event Horizon, partly sci-fi and partly a horror movie. And here the Event Horizon is the name of a ship, and the ship is powered by an onboard black hole. So I'll just give you a few seconds to think about these 3. The scenarios that I've just described, 2 of them are unphysical and 1 of them is perfectly plausible. Which one's which? I'll give you a few seconds. Well, if we think about the first one, the black hole, yes, time might stand still just outside a black hole, but that means that time stands still as seen by an observer some distance away. If you were falling into a black hole, you would not be aware of the fact that time was slowing down. If you were pulled into a black hole, you would simply be pulled straight in. The fact that anybody else would appear to see you stop at the edge of the black hole would just be an effect of a remote observation, not something that was actually happening to the people that were falling in. So no, the Disney version gets it wrong. What about Lost in Space? Well, one thing you have to remember where I started from, the escape velocity is determined by the mass and the distance. If you're escaping quite happily from a planet and then the planet decides to become a black hole by compressing that mass, well, you've effectively got the same mass at the same distance. Therefore, just because you've taken the matter of the planet and made it into a black hole, that does not mean the gravitational pull suddenly goes up. It's the same mass at the same distance. If you're escaping from the planet, actually your distance is increasing ever so slightly. So just because the planet forms a black hole, no, that would not simply pull you back in. So lost in space, wrong. Event horizon. Ship is powered by an onboard black hole. Well, there's nothing in the laws of physics that say you can't do that. If you had a black hole with a mass less than, let's say, about 1 kilogram, then not much energy would be available. The amount of energy you can expect to get out of anything, E equals mc squared. If you start with an energy of less than 1 kilogram, you're not going to get that much energy out. If you start with a black hole with a mass more than that of Mount Everest, then the radiation from the black hole would be very weak. We call that radiation Hawking radiation. It's conjectured that every black hole will slowly evaporate. Just outside the event horizon, particles and antiparticles will be made using the energy available from the gravitational field, and sometimes one of those particles will fall in and one of those particles will escape. And that's what we call Hawking radiation. Hawking calculated that Hawking radiation would be very small for a very large black hole. So if the black hole is too large, Hawking radiation is very weak. But an intermediate sized black hole, more than 1 kilogram, less than the size of Mount Everest, let's take a black hole with a mass of, say, 1 million tons. Then the power in the Hawking radiation, it has been calculated, would be equivalent to the output of hundreds of millions of nuclear power stations. And how long would such a black hole last? Well, you can calculate how much energy is lost from the Hawking radiation, the radiation that you would use to power your starship, and you can calculate that the black hole of that sort of mass would last maybe 1 century or more. So yes, you'd have to replace it every once in a while, but okay, you'd have to replace it every once in a while. A black hole of 1 million tons, it would be smaller than an atom, so your engine room does not need to be very large. You'd just have to figure out how you could capture and use the radiation that would be coming from the black hole. So there's nothing in the laws of physics that stop you doing that. It's used in Event Horizon and it's used in certain Star Trek episodes as well. But what about having shortcuts through space? If we can generate a black hole, now again we're using the two-dimensional analogy. If we have a two-dimensional space and generate a funnel from a black hole, is it possible to connect two of them together such that you can go from one part of space to another part of space and have a shortcut? What that shortcut would look like, remember this is two-dimensional space showing a wormhole in the third dimension. We'd have to think, what does that actually look like in practice? If we've got three-dimensional space, we would need to have a wormhole that goes through the fourth dimension of space. And I don't really know what that looks like, but some people say a wormhole, some people say hyperspace. We could argue, well, they must exist because we've seen them in science fiction like Stargate and Contact and Star Wars and Star Trek. All of these have some sort of a device that allow you to get from one part of space to another part of space via a wormhole or via some hyperspace type concept that allows you to get round this problem of taking so long to move anywhere at the speed of light. And what about time travel? Remember, if a wormhole connects two parts of space, well, given that we're really talking about space-time, doesn't a wormhole also connect two parts of time? Can you not travel through a wormhole and actually go back in time or forward in time? Well, what you think of as a time machine, well, it depends on how old you are as to which particular version of a time machine you relate to. But regardless of what time machine you tend to think about, you can still ask yourself, won't there be a paradox if it is possible to make a wormhole to allow you to travel back in time? Don't you have a problem? What if you kill your grandfather? That means you never existed, so how do you go back in time? Well, Hawking wasn't sure what the answer was, but he proposed the chronology protection conjecture. And it is pure conjecture because there's no way we can prove this. But he said, if it is possible to make a wormhole, that's a very big if you can make a wormhole, then a wormhole that allows time travel will collapse before anything has time to travel through it. In other words, that will keep the universe safe for historians. It'll never be possible to murder your grandfather and change history. A pure conjecture, maybe that's true, maybe it's not. But there is a problem with all of these talks of general relativity and wormholes and space travel and time travel. We don't understand how it all works. General relativity is fine for massive objects like planets and stars and galaxy clusters and possibly the entire universe. But we have another strand of physics which we call quantum mechanics, which works really well for tiny objects like molecules and atoms and subatomic particles. That's the subject of a completely different talk. But if we're going to understand the universe, and in particular if we're going to understand black holes, well, general relativity deals with massive objects and quantum mechanics deals with tiny objects. But what if the object we're trying to understand is massive and tiny, i.e. a black hole? Well, don't we then need both of these? Well, yes, we need, drum roll, quantum gravity. We need to get these two to talk to each other. We need a theory of everything that includes general relativity and includes quantum mechanics. But there is precisely the problem. General relativity and quantum mechanics are not good bedfellows. A so-called theory of everything has proven to be elusive. People have been trying to get these two married together for decades. Even the great man himself, Einstein, had a problem with this. He never really believed that quantum mechanics was the right description of the microscopic world. So he was perfectly happy with his general theory of relativity, but he figured he must be missing something that would allow general relativity to work at microscopic scales. He spent decades wrestling with a theory of everything to try and get things to work. And it turned the handsome young man we can see on the right into, well, the Einstein that we all know and love in his later life. A genius like Einstein couldn't get his head around the problem. So what will it take? Well, the bottom line is we don't know. Maybe there will be some unexpected discoveries from perhaps LIGO, perhaps LISA in a few decades, and maybe that will point the way forward to a better understanding of black holes. Thank you all very much.